Good morning, everyone. I welcome you all for today's session. So, in today's session, we'll be looking at the derivation of torsion equation. So, before we could proceed for the derivation, let me tell you a few assumptions which are important, and these assumptions are made during the derivation of torsion equation. Okay, so it is important to remember these derivation as well as the assumptions because this is very important from your exam point of view. It has been asked many times. You have been asked to state the assumptions made during torsion equation, and also you have been asked to derive the torsion equation. Right, so let us go through the assumptions. So the first assumption here is the material is isotropic and homogeneous. Right, so the material of the shaft is isotropic and homogeneous. So this is a common assumption which is being made for the bending equation as well as the torsion equation. So you need to remember this. Next is plane section remains plane even after twisting. So what does it mean? So in the previous class I discussed that there was a shaft and it is divided into number of elements which are circular discs. So even after applying the torque at the free end, the circular discs will remain as it is. Right? The cross section which was circular, it will remain circular, it will not distort even after twisting or application of torque. Third assumption is torque applied on the shaft is in a plane perpendicular to the longitudinal axis of the shaft. Right? Now suppose this is the shaft, right? It will be having some longitudinal axis. Let me consider it like this. So this is the shaft. So longitudinal axis, let me consider the tip as the longitudinal axis. Now the torque will be applied in this manner, circular manner. So you can just check out if the torque is applied in this manner. So this longitudinal axis is perpendicular to the direction of application of torque. Right? So this is the shaft. Let me consider this as the longitudinal axis, tip as a longitudinal axis. If I am applying some torque in this direction, right? If I am applying some torque in this direction, then you can just try to imagine this longitudinal axis is perpendicular to the direction of application of torque. So that is what he is telling. Torque applied on the shaft is in a plane perpendicular to the longitudinal axis of the shaft. Right? So next, the fourth assumption here is material of the shaft follows Hooke's law. Right? So it follows elastic limit and it follows Hooke's law. Fifth assumption, circular section remains circular even after loading. So these two, that is fifth assumption and second assumption, you can combine it. In the second assumption, what he is trying to tell is the cross section plane remains plane even after twisting, it will not distort. And here the shape of the disc will remain circular itself, it will not distort even after loading or twisting. And the sixth one, the last one, is the shaft considered is straight and is uniform in cross section. So we are going to consider a prismatic shaft. What do you mean by prismatic shaft? It is a shaft whose diameter remains uniform throughout its length. Right? So the shaft considered is straight and is in uniform cross section. So these are the assumptions which are being made while deriving the torsion equation. So with this backdrop, let me begin with the derivation of torsion equation for today's class. Right, so derivation of torsion equation. So in order to start with the derivation of torsion equation, what I have done, I need to consider a circular shaft of length L and a diameter D fixed rigidly at one end. Let the shaft be subjected to a torque of T at the free end of the shaft. Then, right? So I have already drawn the diagram for you. So let me begin with the derivation part. So here now you concentrate on the diagram. right? So consider a circular shaft of length L. So this is length L and diameter D. This is the cross section or the side view. This is the front view. So in the side view I have shown the diameter, which is equal to 2 times the radius, and it is fixed rigidly at one end. Let the shaft be subjected to a torque T. Here I have shown in the cross section that it is subject to a torque T on the longitudinal axis at the free end of the shaft. So what I can say here is I can show the torque here as well, since it is at the free end, right? So this is the free end and it is subjected to a torque T. Now what I have done, I have considered a fiber AB or a plane AB along the longitudinal axis of the shaft. क्या किया है मैंने? I have considered a fiber or a plane AB along the longitudinal axis of the shaft. So this point B I have also shown here on the cross section, right? So I have just projected this, I have shown it on the cross section. Now whenever you are applying this torque, what happens to this? What happens to this position AB? जब आप torque apply करोगे, A will remain fixed because it is rigidly fixed, but the position of B will change because you have fixed this and at the other end you are applying torque. दूसरे end से आप rotate करने की कोशिश कर रहे हो. So B will be shifting by certain distance, right, along the circumference. So that B I have noted it here. So this is the new position of the B. So it is B dash. Then this is connected by a dotted line. Once again the same thing is projected on the cross section. So initially B was here. जैसे ही आपने टॉर्क अप्लाई किया सेंटर पे, then it was here, it will be shifting like this. So B जो था it has become B dash, right? B जो था it has become B dash. So let me write here, it was B initially and it has become B dash. The angle made here at the intersection of AB dash and AB is phi. So this is shear strain angle, and the angle made here at the cross section I have taken it as theta. Right, now after knowing all these things, what I am observing here is the fiber AB has shifted to a new position AB dash because of the application of this torque. So shear strain in this case can be written as vertical, or can call it as transverse displacement divided by vertical height. So what is the displacement? From B it has gone to B dash. So it is B dash divided by L. So that gives me shear strain, right? Transverse displacement divided by vertical height. So transverse displacement here is B dash and height here is L. Right? So that gives me shear strain. So that will be my first step in the derivation. So what I can write here is, from the above figure, that is from the figure what I have explained you previously, shear strain can be written as shear strain. I have denoted it by phi, can be written as transverse displacement, which is B dash, B has moved to B dash, divided by L. So this you can take it as equation 1. Also in the side view, okay, what we are having in the side view, I'll just draw it here. there is something of this sort. Here you are having the center O. So let us say it is B. This is B dash. These two have been connected and this angle is theta. So this is the segment which I am going to concentrate on the side view. So here what I can write for this is length of the arc, length of the arc is equal to, so this distance here, I'll just mark this. So this distance is radius, right? From center to the periphery, this is radius. So length of the arc is equal to radius into angle. We have learned it in our PUC that L is equal to R into theta. So here length of the arc is BB dash is equal to R is the radius and theta is the angle, where theta is in radians. Okay, so this is important. Why it is important? It is important because when we'll be solving numericals, we need to convert degree into radian. Most of the times it will be given in degrees, we need to convert it into radian, right? So what I can write here is, I can take this as equation 2 from equations 1 and 2. We conclude that here also you are having BB dash, here also you are having BB dash. So what I can write here, phi into L, BB dash is phi into L, should be equal to, here also you are having BB dash, it is R into theta. So therefore phi is equal to R into theta divided by L. So this you take it as equation number 3. Equation number 3. Right? Next, from Hooke's law, we know that shear modulus which is denoted by G is equal to, it is the ratio of shear stress to shear strain. So in this case shear stress is tau, shear strain is phi, right? Now therefore if I just rearrange this, phi I'll take it to this side, phi is equal to tau divided by G. So this I'll take it as equation number 4. Now comparing equations 3 and 4, comparing equations 3 and 4, we get, so if you just compare these two equations, left hand sides are equal. So what I can write here is R into theta divided by L is equal to tau divided by G. So if you just slightly shuffle this, what I'll be getting is tau divided by R is equal to G theta divided by L, right? So this is an important conclusion what I arrive at. and this I'll take it as my equation number 5. Equation number 5. Next we'll be proceeding further by taking a circular element in the cross section. So next I have considered an elemental ring. Consider an elemental ring in the cross section at any intermediate radius x from the center. At what I have done in the cross section, I have just enlarged the cross section just to make things clear. Okay, it is the same cross section as the previous one. I have considered an elemental ring. So this is an elemental ring at a distance or at a radius of x from the center, and the elemental ring is having the thickness of dx. So now equation 5 becomes equation 5 becomes so now equation 5 can be written as tau divided by g is equal to theta into tau divided by g is equal to theta into x divided by L. Theta into x divided by L. Right? So therefore tau is equal to g theta by L into x. G theta by L into x. So this I'll take it as equation number 6. Right? And one thing to be noted here is what we need to make a note of is this particular term g theta by L. Theta will be constant for a particular torque. If you apply certain torque, L is constant because it is length, and G is shear modulus. It will also be constant. So when this term is remaining constant, what I can write here is, what this implies is tau is directly proportional to x. That is, shear stress is varying linearly with respect to the radius. Shear stress is varying linearly with respect to the radius. So that variation of shear stress, linear variation of shear stress with respect to the radius, I'll just show it here. So this will be the shear stress distribution in case of a body which is subjected to torsion. Suppose this is the center. What I find is shear stress will be maximum at this particular cases. That is, this will be the shear stress which will be acting upwards. This will be the shear stress which will be acting downwards. This is the center. So you can just connect these two things. It will be varying linearly, okay, with respect to the radius. So what does it mean? It simply means that at the center shear stress is 0, and as you move away from the center it is going to increase, right? So shear stress distribution in this case can be shown like this. You can just show the shear stress distribution. You please mark the arrows. Direction of arrows are also important. Okay, so this is the shear stress distribution when it is having certain torque T applied at the center, right? Now here at the center I'll just write some important boundary conditions. BCs are nothing but boundary conditions at x is equal to 0, that is at this particular point. At x is equal to 0, tau is equal to tau minimum and that will be equal to 0. At x is equal to capital R, that is the maximum radius up to this point, tau will be equal to tau max, right? So this will be maximum. So these are the important boundary conditions which we need to remember, which we require while solving numericals, right? Now I'll come back to this figure. Now in this figure, this particular figure, I have considered an elemental ring. So shear force coming on the elemental ring can be written as shear force on the element considered. So how it is written? It is written as shear stress into area, right? So shear force, because it is element, I'll take it as dF is equal to shear stress. So shear stress is tau, area is dA. So therefore dF is equal to tau. So what is the area of this hatched section in the ring? Area of hatched section is the circumference, which is 2 pi x, because the radius is x. 2 pi x into thickness is dx. So the area here is 2 pi x circumference into the thickness, which is dx. So that is the area which is subjected to shear stress. So therefore dF is equal to, so what is the value of tau? Tau value is g theta by L into x from equation number 6. G theta by L into x into 2 pi x into dx. I'll just write here using equation 6. Right? Now, if I proceed further, therefore dF is equal to g theta by L 2 pi x square into dx. Right? So this will be the shear force coming on the element. Now, whenever you are having an applied torque T at the free end, material क्या करेगा? It will resist this applied torque. Right? If you are trying to rotate it, this is the action. Material आपको कुछ reaction देगा. There will be some resisting torque. Right? That reaction is nothing but resisting torque. So resisting torque on the element, on the element. So that I'll take it as dt. So we know that torque is equal to force into radius. So force हो गया df. Radius of the element will be x. So therefore dt is equal to, df का value ऊपर से ले लो. It is g theta divided by L into 2 pi x square into dx, and this is the radius x. Right? One more step of simplification, dt is equal to g theta divided by L into 2 pi x cube into dx. Right? So this is the resisting torque on the element. So in order to get the resisting torque on the entire shaft, what I need to do? I need to integrate this. So going ahead, I'll be just integrating this part. So resisting torque on the entire shaft is equal to integration of dt from 0 to t. So that is equal to integration of g theta divided by L 2 pi x cube into dx. x का वैल्यू 0 to r से वेरी होगा. Minimum value is 0, maximum value is r. So integration of dt is t is equal to, what are the constants? You please keep it outside. So g theta divided by L into 2 pi is constant. Integration of 0 to r x cube into dx. So T is equal to g theta divided by L into 2 pi. X cube integration is x raised to 4 divided by 4. Limits are 0 to r. So this will be equal to g theta divided by L into 2 pi r raised to 4 divided by 4. So therefore T is equal to g theta divided by L. Now what I can simplify here is 2 ones are 2 twos are, right? So it will be pi r raised to 4 divided by 2, where where pi r raised to 4 divided by 2 is denoted as Jp, and it is polar moment of inertia, polar moment of inertia of the shaft, right? Now therefore T is equal to g theta by L into Jp, polar moment of inertia. If I just rearrange this, I can write it as T divided by Jp is equal to g theta divided by L. So this is once again an important conclusion which I make here. So this I'll take it as equation number 7. So comparing equation 5 and 7, comparing equations 5 and 7, we get, so if you compare equation 5 and equation 7, what we'll be getting is T divided by Jp is equal to tau divided by r is equal to g theta divided by L, right? So this equation I call it as torsion equation. Very important derivation from your exam perspective. I request you to go through this, and we'll wind up with today's session. Have a nice day. Take care. Bye bye.